Hello everybody, I'm Florent Debost, and today I'm going to present ATCON, Attention Consistency for Vision Models. This is a collaboration between Stanford University and Georgia Tech. So when you think about classification CNNs, there are methods that can be used to compute their attention, to show what area of the image are used by the model to make its prediction, and ideally show basically the target object. So for example, there is GradCam, guided backpropagation. The problem is that when the model is not good, the attention maps are also not good, and they can even be contradictory. For example, here, they don't show the same thing. What we want to do in this work is introduce the notion of attention consistency. So if you have a single model, you can have different methods to compute attention that leads to different attention maps, for example, AX1 for GradCam, AX2 for guided backpropagation, and so on. And we want to define a function h that measures the similarity between those attention maps. And we'll use that function during the training stage to improve the performance. For example, if you have this image of a bird, you'd want to classify it as a bird and highlight this region or that region. To do that, you would compute the GradCam, which is here not very good, and guided backpropagation, which here highlights the bird, so that's actually better. And you want to define that function h and compare them. The problem is that they're not very comparable, right? One GradCam is higher resolution because of the model architecture, while guided backprop is showing more the contour of the object and is much higher resolution. So what we do is that we create a mask from this guided backpropagation map, and we use that to mask the inputs and put the mask input again through the network to create a second attention GradCam map. Then we can much more easily compare the first and second GradCam by vectorizing the image and using Pearson correlation. So this is the algorithm that summarizes what I just explained. You can have a look. And here are some qualitative results on Pascal. So this is what I showed earlier. There is not very good consistency between the different attention maps, and they don't even show the right object in most of cases. With the proposed method, the attention maps are much more consistent. They show the correct objects, and interestingly, it also improves the classification results. So for example, this was misclassified as a train, and now it's correctly classified as an airplane. These are some classification results with varying training dataset size, with varying number of training samples per class, and you can see that the F1 and mean average precision improve when the datasets are small. This is also true for the overlap between the proposed detected object and the actual ground truth object, where the performance of the weakly supervised detection improves when the datasets are small. So as a take-home message, you can think that models with poor generalization performance, if you compute the attention maps, is going to have contradictory results. You can use this method to force attention consistency, which acts as a regularizer and improves detection and classification results. Thank you very much for your attention. I hope to see you at the poster. We will have more results on hospital videos and ablation study and whatnot. Thank you. Bye-bye.